The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Thank you for joining us this afternoon, this nice Thursday afternoon. Appreciate FenBC giving Guardian Glass the opportunity to speak with you all this afternoon. My name is Bryce Given, and I will be chatting with you for the next hour about the technical aspects of architectural glass. Assisting me is Jacob Kasbrick, who is the regional architectural manager for the West Coast, or the western half of the US and Canada. And he will be fielding any questions that come through the chat or the question bar on your control panel. Perfect. Here we go. Hopefully you can all see my screen at this point. That's me pre-COVID, top right corner there, back when I got haircuts. It's been about, well, since February since I've had one, so I've been enjoying growing my hair out long. Now you know plenty about me. My name is Bryce Given. A bit of an accent for those of you that are listening in from Canada. I'm born and raised in the Seattle area, and my territory is Alaska, Oregon, Washington, Alberta, and of course, beautiful British Columbia. That's my contact information in the right there, top right. If you have any questions after this presentation, of course, feel free to reach out, and we are happy to help in any way we can regarding glazing or facade questions. This presentation, again, technical aspects of architectural glass, is a condensed version of a roughly 2 to 2.5 hour presentation that was initially prepared by one of Guardian's regional technical advisors. If you or your office is interested in an online version of that much longer discussion, reach out, and we're happy to offer that to you as well. Some quick legalese here. This presentation is provided as a convenience to you and is not to be construed as an assumption of responsibility or liability for design and application choices, which remain the responsibility of the design professionals involved in the project. The material provided is for informational purposes and does not constitute legal advice, modification of Guardian standard warranties, or an additional warranty of any kind. The noted projects do not necessarily implement Guardian products, but many of them do. And the presentation is protected by US and international copyright laws, etc. Here is the content outline for today for the next hour. We're going to talk about glass. What is glass? What constitutes glass? Heat treatment considerations, thermal stress management, structural performance, energy performance, and glazing appearance. We'll continually be referring back to these points as we go through this presentation. So let's start with the introduction to glass. So as many of you are familiar, glass is an amorphous solid, basically a non-crystalline solid, where the atoms or molecules that make up the solid are not organized in a definite lattice pattern. So there's no underlying order in their molecular structure. It's often that we hear about stories of glass on really old buildings being thicker at the bottom than it is at the top, giving some of the impression that over short amounts of time, glass can move, meaning it can be affected by gravity. And if we were talking about millions of years, that might be the case, but oftentimes the reason that we have thicker glass, for example, in old cabins or barns or old factories, the thicker glass at the bottom of the light is due to how that glass was fabricated originally. The ingredients of glass, primarily sand or cullet, and cullet is basically glass that was removed from the manufacturing process, oftentimes the edge of the ribbon of glass that gets cut off after that glass is cooled, prior to that glass being packaged for shipment to customers. So primarily 50% sand, which is silicon dioxide, also known as silica. Soda ash and limestone are added. Soda ash helps to lower the melting point of the glass mixture. However, it's mildly soluble, so thus limestone is added to make the glass insoluble. Dolomite also is added to increase the scratch and chemical resistance and to improve the viscosity. And then rouge, otherwise known as iron oxide, or ferrous oxide, oftentimes is naturally occurring in our sand sources. And rouge is one of the materials that when we look at clear glass, that glass actually looks a little bit green. It's one of the rouge is one of the reasons for that slightly green hue. When you think of low iron glass is produced by sourcing sand with a much lower iron oxide content to begin with, or chemically bleaching or otherwise removing the iron oxide in the mix. Some key properties of glass. So if you think of concrete, for example, concrete has roughly a density of about 2,400 kilograms per meter cubed, about 150 pounds per square foot. So glass is slightly heavier than that. The float bath process involves the glass batch or the glass mix being slightly or gently cascaded onto the top of molten tin. If we think of concrete with a density of 2,400 kilograms per cubic meter, molten tin has a density of about 7,200 kilograms per cubic meter, so much more dense, thus allowing the glass to float on top of that molten pool of tin. There's a thermal coefficient of approximately 4.6 times 10 to the negative 6. It has a hardness of 6 on the Mohs scale. So for example, and the Mohs scale is the resistance to scratching. Gold has roughly a 2.5. Ordinary steel is around a 4.5. Diamond is 10. So the higher the number, the harder, the more scratch resistant the substrate material is. The strength, we're going to talk about the strength of glass later on in this presentation. It's an interesting topic. And then of course the modulus of elasticity. So stiffer materials have a higher modulus value, softer materials have a lower modulus value. The modulus of elasticity of glass is approximately 71.7 gigapascals, 10.4 mega psi. The two dominant properties that we look at, though, structurally, are the weight and the strength. So the glass making process, this is the modern float glass process today. And the facilities that are manufactured or that make float glass are generally constructed in areas where land is flat and real estate is inexpensive. In the image on the bottom left, you can see several rail cars, some trains. Those bring in the raw ingredients where they're introduced into the batch house, around 13 stories tall on the far left side there. The batch house then mixes the ingredients and puts them into the furnace as they're being mixed, which is that lower middle image is what we're seeing there. The ingredients are melted in the furnace at a temperature of around 1,600 degrees Celsius, 2,900 Fahrenheit. And again, they're allowed to cascade gently onto the top of the molten tin at about 1,100 degrees Celsius. And at the far end of the tin bath, closer to the annealing leer, that temperature drops down to about 600 degrees Celsius. The image on the bottom right corner shows a view inside of the tin bath, and you're looking at these guide wheels, and they help to basically help to guide that ribbon of glass through the tin bath, while also at the same time helping to control the speed of the ribbon through the bath. Now, as a glass manufacturer, this is what we think of when we think of glass, and these are the large stock lights that we produce to ship to local fabricators. If we were to think of the size here, so this gentleman with the blue hat, roughly 6 feet in height. The common sizes of stock glass lights today, approximately 96 inches by 130 inches, 102 inches by 144 inches, roughly 8.5 feet by 12 feet, that red outline there. Jumbo size glass is approximately just shy of 11 foot by 17 feet, roughly 3.6 by 5.2 meters. And then there's super jumbo, which is roughly just shy of 11 foot by 20 feet in size. And again, these are the large stock lights produced in North America, in the US today, some with and some without Low-E coatings. So Low-E coatings themselves, most Low-E coatings today are applied with the sputter coat or the vacuum deposition sputter coat process. Many float glass facilities that produce float glass also have a connected warehouse or connected facility that also produces, that applies vacuum deposition Low-E coatings onto the glass. So the first thing that happens here is that glass, after it is cooled and cut to the size required for the fabricator, or required as the stock size, that glass gets cleaned, because any sort of debris or dust or particles that is on the surface of that glass, on the top of that glass, could impede the application of the Low-E coating. So the glass gets cleaned, then it gets slowly introduced into a vacuum chambers. It's essentially a step down process, because the conveyor belt system that moves the glass through the process is constantly, it doesn't stop. So the glass is constantly moving. So each chamber reduces the atmosphere around the glass by about 1/3. And we go from standard Earth atmosphere, roughly sea level atmosphere, to a very, very low pressure, mostly argon atmosphere. In the sputter coat chambers, each pair of cylinders or each pair of plates represents a different metal layer on the Low-E coating. Those cylinders or plates get enveloped in a plasma, roughly visualized by that middle lower image there. And so each layer or each pair of plates or cylinders that the glass passes under, those plates or cylinders deposit an additional layer of metal onto the top of that glass. Some Low-E coatings may have 5, some may have 7, some 12, some 25 or more different layers of metal in their Low-E coating stack. I'll go back real quick. That nugget there in the top middle, that's representing silver. Silver is the workhorse of Low-E coatings. There's single silver, double silver, triple silver Low-E coatings. And the residential industry, if you hear terms such as a double Low-E or a triple Low-E, oftentimes they're referring instead to how many layers of silver are in the Low-E coating stack. So we talked about glass Low-E coatings. Let's look at heat treatment considerations for a moment. How is heat, what is the process for heat treatment, and why is heat treatment done? So the strength of glass is dictated by its tensile capacity. If we look at a cut through of a glass light, when the glass gets heat treated, the idea is that we are putting the outside layer, the perimeter of the glass, in compression, thus basically by having that perimeter be cooled quicker, and then the inside of the glass is put into tension because the inside cools a little bit slower. So let's look at that for a moment. So when we take the annealed glass, or rather when the customer, the fabricator, takes the annealed glass, that glass, after it is cut to the size required for the IGU, gets heated up in the tempering oven to approximately 620 degrees Celsius. So the glass is warmed up, and then it is cooled or quenched by blown air onto the top and the bottom surfaces. Now, if there's a Low-E coating on the top surface, yes, that can complicate the quenching process. The result of this cooler air on the hot glass, much like if you were to broil some brownies in the oven and then bring them out, is that the perimeter of the glass is in compression and the inside is in tension. And then as the whole glass light normalizes to regular air temperature, the compression and the tension pressures inside the glass light remain. So ANHSFT, so annealed, heat strengthened, and fully tempered. So annealed glass is what all float glass starts off as. Heat strengthened and fully tempered are fabrication processes done to make that glass stronger and more resilient, or to make it into safety glass, for example. So the bending strength of heat strengthened glass is approximately 2x, 2 times that of standard annealed glass, and fully tempered glass is roughly 4 times that of standard annealed glass. With regards to cutting the glass needs to be cut before it is heat strengthened, before it is tempered. I have heard stories of folks polishing or grinding or cutting heat treated glass, and it is not something that as a glass manufacturer we recommend. Shard retention. So back to that image there in the bottom left corner. Fully tempered glass, also known as safety glass, as you're very familiar with, when it breaks into lots and lots of very small kernels. Heat strengthened glass does not break into the same pattern. Heat strengthened glass instead breaks closer to that of what annealed glass does. So if there is breakage, tempered glass without an inner layer can fall out of the glass opening, fall out of the window opening. Heat strengthened glass, yes, it can fall out, but typically that breakage pattern propagates to the perimeter sealant, which hold those shards of glass in the frame. Now, as far as safety glass is concerned, the glass doesn't have to be tempered if it is laminated. Safety glass can use annealed plies with a laminate or heat strengthened plies with a laminate. Optical control. So let's look at this for a moment. This is known as roller wave distortion. We've all seen this. Generally, we hope that when we do see it, that instead of that wave running vertically like you do in the middle of that image, that instead it runs parallel to the ground, parallel to the surface of the earth. So what causes roller wave distortion? So when the glass is heated up to around 620 degrees Celsius in the tempering oven, it becomes ever so slightly soft. Each one of those spheres represents the roller wheels that move that glass through the furnace. And if we were to look at the top plane of the glass and just focus on that top plane for a moment, and we're going to increase its amplitude a little bit to make this discussion easier. We're looking at peaks and valleys. And these peaks and valleys are what we see, or rather it's the reflection off of light off of these peaks and valleys is what the eye picks up when we see roller wave distortion on buildings. So internally, we target limits of roughly 0.003 inches, 0.005 absolute inch limit. These equate to around 0.08 millimeters, 0.13 millimeters, and this is for commercial grade thicknesses of 6 millimeter, 8 millimeter, and 10 millimeter substrates, or quarter inch, 5/16, and 3/8. Now, the roller wave control along the leading and trailing edge, though, is more difficult. And so this 0.03 or 0.005 target is relaxed leading and trailing edge, often to around 0.008 inches. As mentioned previously, it's the reflectivity off that wavy plane of glass that our eye picks up. And so more reflective glass will amplify what our eyes see, and less reflective glass will, of course, mute what our eyes see. This is, again, why we recommend that when glass is installed on buildings, that the roller wave be oriented so that it is parallel with the ground, so that when you are walking by it, it is less apparent versus if it is vertical. And if it's a vertical application, that it is more apparent. There's also what's known as bow and warp. So standard specification for heat strengthened and fully tempered glass presents limits for local bow and overall bow. In the US and Canada, our commercial and residential coated glass customers are expected to limit bow to no more than half of ASTM C1048, so approximately 0.79 millimeters or 1/32 of an inch per foot. And then our, as far as center kink goes, we prefer that it be limited to no more than 0.001 inch per foot. There. Heat treatment considerations, nickel sulfide and heat soaking. Many of us have heard of spontaneous breakage, and those new to the glass industry might not be aware that glass can spontaneously break. With nickel sulfide, one of the other things that is a cause for concern is if there is a nickel sulfide breakage, oftentimes that breakage, if it's on an inboard uncoated light from an unknown float manufacturer, that breakage may be associated incorrectly with the outboard coated low E light. And so that's one of the reasons that we want to be careful about how we talk about nickel sulfide breakage. With heat strengthened and annealed glass, the risk of nickel sulfide breakage is very, very low, essentially none. With fully tempered glass, there is a possibility for breakage. So what is nickel sulfide or NIS? Basically, during the heat treatment process, the nickel sulfide inclusion, if it is present, it can convert to an unstable state. Now, with the application of heat and or passage of time, warm seasons, colder seasons, that inclusion may revert back to its stable state. Now, in the process of reverting back to its stable state, it expands in volume, which produces additional stress on the surrounding glass, which can cause that NIS to cause that glass to break. There we go. Sorry, trouble with my mouse cursor. If that inclusion is in the perimeter of the IGU, meaning it's on the surface of the light, in the compression area, there's a lower risk of breakage. If that inclusion is in the middle of the light, in the tension area, there's a higher risk of breakage. You can see what a breakage pattern looks like there on the bottom right. Now that cat's eye pattern does not necessarily mean that nickel sulfide is what caused the breakage. Heat soaking. So heat soaking is a process that fabricators offer. It's especially useful for projects utilizing very large IGUs, projects where the replacement of glass after installation might be difficult or very cost prohibitive, or projects where broken glass after installation might not be, obviously it's not desirable anytime, but broken glass after installation could result in a bit of a media frenzy. Heat soaking is most notable in relationships to fully tempered glazing applications with intense reliability requirements, such as structural glass members, glass floors, point supported glazing, and or panels with expensive replacement costs. Back to this chart again, if we just a recap, fully tempered glass, approximately 4 times the strength of annealed glass. Heat strengthened glass is a good middle ground to if tempered glass is not required, but the IGUs are large enough that we want to resist more thermal stress. And we are also looking for glass retainage should that glass ever break, and we want to retain those lights in the IGU. Moving on to thermal stress management. When we talk about thermal stress, the concern is the excessive temperature difference, or delta T, delta temperature, within the surface area of the glass. So some scenarios that we typically see is cool captured edges versus warm center areas, cool shadowed areas versus warm sun exposed areas, cool areas versus warm areas across surface area at sunrise, intensified differential temperatures based upon energy absorption of tinted glass, And that's and when we refer to tinted glass, we're not talking about a coating on the surface, but typically we are talking about a through body color. The glass itself has a tint to it. And then number 5, intensified differential temperatures based upon impeded ventilation. So let's look at center of glass for a moment. So you got your glass light, you've got your frame, you've got warmer center of glass there. And if you're somebody who likes arrows, I appreciate arrows. I've included that inset image on the bottom right there. So what can happen is when the glass warms up, the middle of the glass wants to expand because it gets warmer, and there's a thermal coefficient of friction, thermal coefficient causing that glass to expand, but the perimeter stays cool. And the perimeter can stay cool because of its proximity to shadows from window mullions or other building elements. It can stay cool because of proximity to the aluminum frame system. For what reasons that the perimeter wants to stay cool. But what can happen is you have a buildup of stresses. Another reason that you might have thermal considerations is if there's differential shading. That green thing in the middle of the screen, that represents a tree causing shadows on that glass. And so differential shading can cause for internal stresses to build up at the perimeter of the shaded area versus the non-shaded area, which can cause the glass itself to want to slide, basically the glass molecules to want to slide past themselves. And of course, warm areas, when the sun comes up, again, same issue, can cause the middle of that glass to want to expand. And then spandrel applications or tinted applications versus clear glass, same thing, especially if there's an opacifier or a shadow box or reduced ventilation on the interior side of that glass, it can cause heat retention and heat buildup. So scenarios. So cool captured edges versus warm center areas. So frames with light colors and or intensified reflectivity, climates with particularly elevated temperatures, larger glazing assemblies fall into that category. Exterior sunshades, overhangs, projections off the face of a building, such as architectural features or adjacent trees, signage, or surrounding construction can all lead to scenario number 2. Severe morning temperature swings, even if rising from extremely cold or merely cold, you have a buildup of solar heat gain from the direct energy from the sun, can lead to condition number 3. Tinted, fritted, or coated glass, whether it's a ceramic frit on the inboard surface or a silicone emulsion, a paint on the inboard surface. Applied films, and this is one of the reasons why third-party field-applied post-construction films can result in the loss of an IGU warranty if they're applied to either the outboard or the inboard surface of an IGU. And then laminated glass, those can all result in situation number 4. And then situation number 5, internal shading devices and middle lights of triple or quad pane glazing. We always suggest that middle lights of triple or quad pane glazing be tempered to resist breakage. Moving on to structural performance. So we had talked about randomized breakage, and this is interesting when we look at the actual strength of glass. So the strength of glass falls somewhere along this bell curve, and it is not reasonable or it's not practical to be able to actually measure the strength of a given light after it has been fabricated, after it is produced. So somewhere in here is your light of glass on your building. And that light of glass might be in the upper portion of the curve. So it is incredibly strong and it won't ever break. But of course, we won't be able to identify that particular light of glass compared to a light of glass that may fall down here towards the weaker end of the spectrum or even in the middle of the curve. 8 in 1,000 is the foundation for which ASTM E1300 is based. 1/1000 breakage is recommended by Ghana for overhead skylight applications. As a good practice in skylight applications, a laminated inboard light is that uses heat strengthened glass, not tempered glass, is what we often will recommend for most applications because of this breakage concern. So ASTM E1300, standard practice for determining load resistance of glass in buildings, is the leading domestic standard on the structural performance of architectural glass glazing. So applications beyond the scope of ASTM include fritted, patterned, drilled notch, point-loaded, point-supported glass, glass balustrades, IG units without supported edges, and other special configurations. Also, situations beyond the scope of ASTM are best addressed through FEA, or finite element analysis computer modeling, and the glazing consultants working on your projects can help with that. We'll talk a little bit more about FEA here shortly. So ASTM E1300, as far as what a glass manufacturer can provide, is we can look at wind loads, we can look at deflection, as long as you have a vertically oriented four-side supported, meaning not butt glazed, but four-side supported with a mullion at the top, the bottom, and the left and the right, supporting all four sides. And we can look at the wind load calculations to determine how much that light or that IGU may deflect given the project's parameters. Now, finite element analysis at a very high level essentially divides up the situation into a bunch of smaller, more manageable calculations, more manageable portions. The applications are beyond the scope of ASTM E1300, and modeling by a registered design professional experienced in the structural analysis of glass or glazing is required and highly suggested in those cases. Now, supporting guidance. So frit application, ceramic frit application can reduce the load resistance of glass by approximately half. PVB inner layers exhibit reduced strength and stiffness at extreme temperatures, so around over about 50 degrees Celsius. Frit in contact with PVB should be reviewed to validate suitable load transfer from the frit, from the glass surface, to the PVB, to the inboard light. IG units should be continuously supported along all edges when possible. Overhead glazing should not be treated as a walkable surface regardless of what the building developer requests. Overhead glazing with a tempered upper pane may offer a level of hail resistance, and overhead glazing skylight should implement a laminated, heat-strengthened innermost pane. And glass balustrades and fins should be comprised of laminated glass. Not all codes require this, though. Tempered glass is oftentimes what most jurisdictions require. But again, with regards to glass fallout, if you have a balustrade, say on the second floor of a mall or the 30th floor of a residential high-rise, if that glass should break, even though it's broken into a bunch of little kernels, those kernels still can remain together until they have impacted something below. A laminated inner layer helps to keep everything together and is safer overall. Point-supported glazing requires an intensive engineering design process, and of course, interior butt glazing requires special deflection control as well. Let's talk about deflection for a moment. So generally, as a safe guideline, a peak deflection limit of 3/4 of an inch is a reasonable starting point. Advanced analysis is recommended if proceeding with glass deflections beyond 1 inch. Many of Guardian's customers will limit deflection to about 1 inch. However, with the onset of oversized jumbo glass, over 50 square feet, over 100 square feet, we are seeing deflection in excess of 1 inch, sometimes 1.5 inches, sometimes more. It's always looked at a case-by-case basis. So a reasonable starting point is L over 100. But advanced analysis is recommended if proceeding with glass deflections in excess of L over 50. And it should not be permitted to deflect more than its structural capacity, and glass edges must be captured or bonded to ensure reliable retention of the glazing panel with a reasonable margin of safety under all design considerations. And then for skylight applications, it's very important that the glazing must not deflect in a manner that would provide for uphill drainage, which would then allow for water retainage on the surface of that light, or potentially water penetration into the frame system. Structural silicone sealant is also something that is important to consider. So when looking at structural sealant applications, review the applicable drawing specifications and design load considerations and conditions. Want to make sure that the sealant supplier agrees with the sealant bites and their implementation detailing, agrees with the provisions against pullout of captured edges positioned opposite from structural sealant supported edges, and affirms the warranty coverage for the application. As far as IG fabrication goes, the IG unit seal is part of the load path, adhering the outer pane of the glazing to the framing. Edge deletion of low E coatings in an SSG application can be and is important so that the load path does not travel through the low E coating. Most low E coatings will get edge deleted anyways, especially if they have silver in them, but it's an additional consideration in SSG applications. Setting ledges can help to carry the weight of the IG unit with the structural silicone delivering additional support, guarding against outward tipping, resisting suction, wind pressures, and so on. Factory glazing allows for more tightly controlled conditions and facilitating quality, and is particularly important for four-sided structural silicone systems. Let's look at structural performance for a bit. Sorry, just look at structural performance. We're going on to energy performance now. So generally, predominantly, the low E coating gets placed onto the number 2 surface, so outboard of the airspace or argon space. The benefit here is that it is between the solar energy source, the sun, and that airspace. Now, different configurations of IGU all use the same numbering system. The outermost face, the outermost surface, is always numbered number 1. And then it increases going on in. So if you have a monolithic light, you've got surfaces 1 and 2. If it's an IG unit with a laminated outboard, you've got surfaces 1 on the outboard, surface 2 and 3 are against the inner layer, surface 4 is outboard but facing the airspace, and then surface 6 is on the interior. Several ASTMs look at testing or provide test guidance and test methods for IGU performance, for fogging, and insulating glass performances and evaluations. PIB primary and silicone secondary seals are standard. The PIB goes between the spacer and the glass, and the silicone, which has more structural capability, connects the glass to the glass, bypassing the PIB spacer, PIB secondary sealer, primary sealer. With regards to solar heat gain and U value and electromagnetic energy, when we think of sunlight, predominantly we think of visible light transmittance, visible light in the 380 to 780 nanometer range, but we're also looking at infrared and UV light. Solar heat gain is the transmission of electromagnetic energy from the sun. U value is, and preferably we're talking about winter nighttime condition here in northern climates. U value is the energy transfer caused by an ambient temperature difference. So we're going to look at solar heat gain for a moment. So if we consider the full spectrum of solar energy, 49% of visible energy, 49% of infrared energy, and 2% of ultraviolet energy adds up to 100. So our sunlight is producing 100% solar energy. Now, if we have a material, a transparent material that blocks all but 37% of that solar energy, the result is that we have a solar heat gain coefficient of 0.37. SHGC is the decimal description of solar energy transmission. Now, for those that have been in the industry for a while, you may be familiar with shading coefficient. We still oftentimes see shading coefficient listed in specifications. The difference between shading coefficient and solar heat gain coefficient is that shading coefficient is calibrated to the solar energy transmission of 1/8 inch thick or 3 millimeter glass, which has a shading coefficient of 1.0. Solar heat gain coefficient is not calibrated to a physical sample like shading coefficient is, but rather solar heat gain coefficient is the direct and indirect solar energy transmission represented in decimal form. A U value, again, is the energy transfer caused by an ambient temperature difference. A lower U value results in a higher R value. They're the inverse of each other. So for example, if you have a U value in BTUs of 0.25, you will have a R value of 4. A U value of 0.10 is an R value of 10. Energy transfer divided by time glazing area, time temperature difference. Now, as far as low E coating placement is concerned, if we look over on the right-hand side, you'll notice that there's no difference in U value, whether that low E coating is on the number 2 surface or the number 3 surface. However, if that coating is on the number 2 surface, from a solar heat gain perspective, because that coating is outboard of the airspace and protecting that airspace from more solar heat gain transfer, you have a lower solar heat gain value for the IGU. If that low E is on the number 3 surface, which is not uncommon for projects in Alberta, for example, that low E coating will provide a higher solar heat gain coefficient for that IGU. So again, lower solar heat gain value blocks more heat from the sun, and a higher solar heat gain allows in more heat from sunlight. And generally, with U value, lower is better. It's better insulation. Center of glass versus window unit, whole unit performance. So the glass manufacturer, most of the energy performance reports that we provide are based on center of glass metrics. As a float glass manufacturer, we do not know what seals, we do not know what sealants, we do not know what window systems are going to be used every single time. So all of our values are based on center of glass. The thicknesses, the colors, the surface treatments, those are included in our calculations. We can also include the dimensions of the spacers, such as the 1/2 inch, 5/8, 3/4 inch, or roughly 12.7 millimeters, 16 millimeters, or 19 millimeters, and whether it's filled with air or 90% argon, 95% argon, etc. We can also calculate for inner layers, as well as installation angle and how that will affect the overall U value center of glass. As far as whole unit performance, there are some loose translations, but each facade system manufacturer or window manufacturer or storefront manufacturer oftentimes has guide tables that they can provide that will give a rough translation between center of glass performance and whole unit performance. Generally speaking, your visible light transmission in a whole unit is roughly 10 points lower, 0 to 10 points lower, because the frame will block visible light transmittance over the whole area. Oftentimes, solar heat gain coefficient is slightly lower because the window frame will block some of that solar energy. And as far as U value, generally the U value, especially with an aluminum system, will be higher compared to the center of glass value because there's thermal energy that can transfer through that window frame system. Let's look at appearance for a bit. Visible light transmission. So visible light transmission is the percentage of solar energy from the electromagnetic spectrum that's in the visible range to humans, 380 nanometers to 780 nanometers. Birds have a slightly broader spectrum that goes a little bit further into the UV spectrum, the ultraviolet spectrum. That chart on the bottom there is showing basically a table difference between spectrally selective low E glass and low E glass that is designed to block all solar energy, as much solar energy as possible. So spectrally selective is called spectrally selective because it selects the part of the spectrum in the visible section and tries to allow in as much of that light as possible while blocking as much infrared energy as possible. Quick visual comparison between visible light transmission and reflectivity. So on the left-hand side there, 68% visible light transmission with 11% outward reflectivity. Compare that to the far right side at 18% visible light transmission and 30% outward reflectivity. More outward reflectivity provides more of a controlled aesthetic to the design, to the facade, in that the ongoings, everything happening inside the building, aren't as visible. It also thus gives more privacy. Nighttime conditions, though, anytime you have a situation where the amount of interior lighting is greater than the exterior daylight conditions, you will see through the glass, and not much we can do about that situation from a design perspective. For daytime appearance, we always suggest looking at glass samples elevated or at least on some sort of vertical angle with a dark background. This is how most of our buildings are oriented. Internal environments are oftentimes much darker relative to the exterior daytime daylight environments. One way to do this is to use a prop-up box like this with a dark background so that you're seeing the reflected sky off of that glass. Another great way of doing this, of course, is to get local examples of existing buildings that have used the type of glass and low E coatings that you are looking for. For nighttime appearance, view hand samples on a white background or with the light source behind it. Here's another example, daytime versus nighttime. Both of these examples use a reflective outboard low E glass, roughly 30% outward reflectivity. And you can see the visual difference between daytime and nighttime. At nighttime, again, because that interior lighting source is brighter than the exterior source, the outward reflectivity on that glass is not that apparent. As far as the L star, A star, B star color system, this is what we use to look at the colors of glass. And glass has three colors. It has its outward reflected color, its transmitted color, and its inward reflected color. The chart on the left there is meant to be a three-dimensional representation on your 2D screen of the tables that you oftentimes will see in glazing performance charts, which I've included down there in the bottom. You have your B star axis, which is your yellow down to blue, and you have your A star axis, which is green and red. And then there's the L star axis, which is the darkness and lightness of the glass. Your hue color is where does that glass sample fall in the A star, B star axis. And saturation is how far away from the center or origin point does that sample fall. And then lightness, of course, is the vertical L star axis there. The delta E is a combined number that we use to look at the color variation between glass samples. And we can provide delta E's for outward reflected color, for transmitted color, and indoor reflected color. If you have an existing building with glazing that is, say, 20 years old and that glass and or coating aren't available anymore, typically what we will do is we will look at the outward reflected delta E and the transmitted delta E to try to come up with the most consistent color match. If it's a skylight application, then we'll look at the transmitted delta E as well as the indoor delta E. And generally speaking, your B star and A star axis delta E's are a little bit more important visually speaking compared to the L star axis as far as what our eyes pick up. An average casual viewer can notice a delta E color difference of around 5 to 6. ASTM limits the installed delta E of an IGU to a limit of 4.5. Internally, Guardian aims for much tighter tolerances than these. And for many of us that are in the architectural industry, we're looking at colors, we're looking at buildings, we're looking at samples on a regular basis. We can probably see delta E's tighter than 5 to 6. And if you have two samples side by side at the far end of that allowed delta E, you could also probably see a difference as well. As far as spandrel glazing is concerned, there's three predominant types that we see most often in our market. Monolithic spandrel, which is what you see there on the far left side. It's just a monolithic piece of 1/4 inch fully tempered glass with an opacifier on the number 2 surface. This spandrel oftentimes is not meant to harmonize, not meant to blend or look the same as the vision glazing. It's an economic value engineered option, commonly used for high-rise residential. The middle example there is with tinted glass, where the same tinted low E glass, low reflectivity because the glass is tinted, so it's absorbing more solar energy. Tinted glass with a low E coating used for both the vision and the spandrel can provide good harmonization. And then reflective glass, which is what you see on the right, reflective low E coating on a clear glass substrate used for both the spandrel as well as the vision glass with a nice opacifier on the number 4 surface. That's also a good option, although both the option in the middle and the right are going to be more cost to the project at construction compared to the monolithic spandrel glazing on the left. That is the condensed version of technical aspects of architectural glass. Thank you all for listening in. At this time, I'm not sure if there were any questions, or if there are questions, happy to field any if anybody would like to speak up.
Yeah, Bryce, nothing in the chat box. You were very thorough,
Okay.
so if anybody has anything at the moment, I'll bring it up.
Well, I give thanks to the technical engineer that wrote the presentation. Again, if anybody is interested in a 2-hour, 2.5, or 3-hour version that goes into a much deeper dive, we can of course provide that. If anybody is interested in the architectural version of this that I give to architects, and we have lots of examples of local projects, and it's a bit more upbeat in nature, happy to give that as well. Thank you all very much for your time.